let me get started. Basically, we are modeling data, and there are two kind of data, as I explained in one of my earlier sessions. In one case, where the data points are associated. If you look in a time series data, for example, so every next data point is associated with the current data point, or in an image where left and right pixels are associated with the central pixel. So if you move these pixels around, the image will get distorted. So this is the kind of data where there is some kind of association. And then there is other kind of data where there is no association, like when you have a table, like Excel table, where you have rows as data points and you have columns. So even if you move some rows up, down, swap them, nothing much will happen basically. So all the results should remain the same. Now, in case of the data, when there is an association, we need to model them differently. And one particular example is of text modeling. So text is made of words or a sequence of words. And most common languages, they run from left to right. And there is a strong association between these tokens and these words. So one of the requirements of this sequence to sequence modeling was modeling this kind of data or a sequence when there is a association. And what was the second requirement? In general data, like in images, and you have Excel table, when you are doing machine learning, so you have a data set, and data set is made of data points. And in general, all the data points are some sort of same format. If you are doing image recognition, then you can always scale all the images to the same scale before passing these images to the image recognition without losing any feature of the image, without losing quality of the image. And the same thing can be done with other kind of data also, where we have, when you have an Excel data sheet, then you will know that all the rows have the same number of columns or the same entries. And they have the same information. But in case of text, there is one difficulty. If we look at any paragraph, it is made of sentences. And these sentences have different length. Some sentences are long, some sentences are short. So we are looking for a machine learning framework which can incorporate these two kind of requirements. One requirement is the association between the data points or the sequence. And second requirement is that input data points may be of different size. And this is exactly where the this sequence to sequence model comes. So it gives us a procedure by which we can map sentences of different length to one fixed length vector. And once we are there at the fixed length vector, we can do usual machine learning. So this is the background of and motivation for the sequence to sequence modeling. So now let me go to the agenda. So I will talk about recurrent neural network. And then I will talk about vanishing gradient problem, long short-term memory, and sequence to sequence model. So many of these terms are pretty advanced and need some background, but I will try to cover as much background I can to explain that how these things work. What is the recurrent neural network, and what are the type of problems it has, and what problems it can solve, and what problem it has. So look at a common neural network. Common neural network is made of neurons, artificial neurons, and they are very much motivated from the neurons in human brain. So some of the main properties of these neurons are that a typical neuron has multiple inputs and single output, either in human brain or in machine learning. So what happened that when a neuron has multiple inputs, so before processing these inputs get multiplied by some weights, a matrix W as is written in the equation. And then xi is the input vector, ith data point, and its capital X means X is a full-fledged vector. So dimensity can be whatever is needed for our case. W is a matrix, X is a vector, and B will be also a vector correspondingly. So this is the type of output yi we get from a neuron. So neuron, what it does that it adds up input, all the inputs, adds some bias to it, applies some non-linear function which is called activation function or it, and gives output. Here f is a non-linear activation function. If you just remove that f, consider that just one, this is nothing but a linear regression in that case. So it's just a non-linearity. And in the lower picture, you can see that how this is happening. The weights are getting multiplied to the input and they are added, and then we add one bias on it, and then activation, and finally we get the output. So machine learning models, particularly supervised machine learning model, they try to learn a mapping between input and output data. And once this mapping is learned, then we can find output for any unknown input. For example, image classification, we have a set of images in 10 classes. And if we have a large data set where there are thousands of images of every class, so we can train a neural network model for it. And once the model is trained, then when we get a new image of one of these classes, which was not in the training, we can immediately get the output and label for it. So the idea is to learn the mapping between input and output. So this is the common type of neural network, feed forward neural network, you can say it. So in this case, what happens that again, there are many neurons in your layer, and then we stack these layers on top of each other. So leftmost layer is called input layer. It takes input data, and the rightmost layer is the output layer. It gives output, and any layer which is in between is connected to left and right layers. So basically, left layer feeds the current layer, and current layer feeds the next layer. But in this common type of neural network, which are used in image recognition and many other applications, so generally, the data points are independent in the way that we can pass images. Now consider our data set is made of images. So we can pass images in any order. Our result will not change. So we have a neural network architecture. We are passing images to it. So every time we pass one image, the weights inside it get updated. They're tuned, because we are trying to match the prediction with the actual output using the backpropagation algorithm. So what is it? I'm giving an example of image recognition. What is happening is that we start with the random value for the weights. Okay, and this neural network will map every image to some label. Now we match that label with the actual label using a loss function. And from that loss function, we try to find that how much we should tune the weights so that the predicted and the actual output they match. So here now, but in recurrent neural network, it's a bit different. If we take a single cell of a recurrent neural network, and what we expect it to have is the memory. So we expect it to remember that what was the last data point. So in this situation, what happened that this left cell is the cell of RNN. So it takes output from the previous state or the previous time and add that in the current input. And it uses one state called the hidden state H, which is some kind of memory. So it is keeping track of the data point, what it has seen before. So it's a RNN cell and data is passing through it. And the value of H is getting updated as more and more data passes through it. So that means it has some kind of memory and it will help us in sequence modeling. For example, in case of text, when there is a sentence, when we say that the sky is blue, the first time when the will go, the H will take some value. Then sky, then again H will change its value. And the blue, then it will change its value. So it is adding into the knowledge of that hidden state. But there is a problem with this, which is called, and the equation is simple on the top right corner. What you can see here is the hidden state HT at time t. It depends on the current input xt and the previous hidden state ht minus 1. And W and U are weight matrices and B is bias. So here we have two weight matrices, unlike in the earlier case. And G is a nonlinear activation function, most probably a sigmoid or 10H function. And once we have the memory state or the hidden state, from that we can immediately find out the output by applying some nonlinear activation function. So there are two ways we can represent this RNN cell, recurrent neural network. One is this compact form, as is shown in the left, and second is the rolled out form. So rolled out, essentially it is the same cell, but what is happening is that we are showing it at different times. So now the sense of time also comes in this RNN cells sequence. When we say that there is sentence of 5 tokens, so when first token goes to it, we say that a time is 1. When second token goes, we say the time is 2, and so forth. So we can draw these cells for different times as they are shown in the right. It's called rolled out version. And it is easy to see that what at the time t1. For example, you can see that when we give input x1, it actually takes h0 also. And for x2, it takes h1 also. And this is the same thing explicitly here it is made. And you can see that finally our state is ht plus 1 or whatever the last sentence is. So this is recurrent neural network, but it has a problem. And that problem is again in different way also we can depict the same thing in this way also. The W and U matrices are there and H and X are variables. X is the input, H is the hidden state. So how we train this RNN? Initialize the weight matrices WU and hidden state vector HT minus 1 or whatever the starting time we consider. Then we compute HT, keep doing till the sequence ends. So now I am repeating this thing. What is we are doing that we have W matrix, we have U matrix, we have bias. We set some random values to these. And H also we can set some random value. Now we pass the input X and then X, let us call this X1. Then we get the H1. Now when we pass X2, we give H1 also as input. And then we keep doing this thing. And then we compute loss, compute gradient, update weights. So this is exactly as is done in any machine learning exercise. So this is a back propagation learning. So how it happens is that output y hat is a function of input x, and when f is a function, non-linear function. We can simplify it. We can use the same function for like in case we have many layers also. So it will be complex, but basically y hat will be a function of input. And so this is the mapping between input and output. The y hat function is a mapping between input and output. Then we compute the loss function. What was the actual y and what was the predicted y? So in case of regression, like we use mean squared error, and for classification, we use cross entropy, and there are many other loss functions also. So the idea is to minimize these loss function. So if we do some calculus, some basic calculus, we can find it out that if we update the weight in this way as is shown in the third equation, then it will guide us in reducing the loss. So what we are interested in is the gradient of loss function with respect to the weights. Now, what is happening is that there are layers, 1, 2, 3, many layers, and output is at the end. Now, if we try to find the gradient of the weights which are in the output layer or very close to that with respect to loss, we will get a significant gradient. But when we try to get the gradient of loss with respect to weights of the layers which are very close to the input layer, so what happens that there is a chain rule. So we can't get the gradient directly from the output to the weights of the first layer. So we have to do the back propagation. So there are many gradients in between. We have to multiply them to reach up to the weights of the first or the beginning layers. And when these gradients are small and we are multiplying them, then we expect they will go to 0. So what happens that when we have a text sequence, it's a very long sentence, then the RNN which we have a common RNN, it doesn't remember very far in back. So sometimes we say that I reached Chennai, and after reaching, I have done this and this job. So there is a Chennai in the very, so that may be important for the later references. So, but this LST, this common RNN forgets that due to this vanishing gradient problem. Because the flow of information is not much from the output layer to the starting layers. So in order to fix that, a new architecture was proposed, which is called LSTM, long short-term memory model. So what we are trying to do is that we are trying to control the flow of information in both ways, particularly back propagation. And we are making sure that the gradient, they never vanish. At least there is a minimum value of gradients which remain there, so that there is a memory. Even if there is a very long sentence, we have some information about the words which are coming in the beginning. So this I already explained that the simple RNN suffer from short-term memory. If a sequence is long enough, they will have a hard time carrying information from earlier time step to the later ones. If you are trying to process a paragraph of text to do prediction, simple RNN may leave out important information from the beginning. So during back propagation on simple RNN suffer from the vanishing gradient problem. And here it is shown in the mathematically, particularly you can focus on the third equation. So it's a gradient with respect to weight. And then you can see that there is a multiplication of all intermediate gradients. And if any of them is small, then the gradient will vanish and the network will not learn much. So this is how the back propagation actually works. You can see that there is the input layer, there is a hidden layer, there is the output layer. And then finally we get the output. So the difference between the actual output and the predicted output is called error. So we are trying to minimize that error with respect to the weights. So we are trying to find out what values of weights we should use so that we get minimum error. So flow of information is from output to the input. Now here comes the LSTM, long short-term memory. And this architecture was proposed in 1997. Even before that also some ideas were there, but proper paper came in 1997. And this is one of the highest cited paper in computer science and AI. So it has changed many things, and this model ruled, I think, from that time to all the way up to 2017, I mean, few years back. So this was the paper, and they clearly had this, the problem mentioned, that what is the problem. And they gave this architecture that if we use some gates in this RNN cell, so we can control the flow of information. I think it is as revolutionary as I can say that, like in case of transistors. We can create very complicated system by just, there were diode, but when someone put the gate in between, then the whole thing exploded, and the tremendous technology came from that, just using those gates, which we are still using these. So here also, this is the same thing, that these gates, so there are, okay, apart from gates, this LSTM, they have another state also, which is called cell state. So common RNN had one state, which is the hidden state or the memory state H. But this LSTM has another state also, which is called a cell state or C state. So look at the left part. This is a common RNN, where it takes the HT-1 and XT when it is processing at time T, or the current time somewhat, and it is giving some output. But LSTM packs uh, three gates inside it. In fact, four gate. One is called a forget gate. From left, it's a forget gate, input gate. It's a cell gate and output gate. The small yellow boxes close to bottom, they are gates. And all of them consume current input data XT, as well as past hidden state HT-1. So you can see that this HT-1, which is a horizontal line at the bottom, the thick black line, it is branching out. Basically, it is feeding all these four gates. The XT and HT-1 both are feeding all the four gates. Now these gates will be like on and off type of situation, where the forget gate, input gate, and output gate, we apply sigmoid on it. So sigmoid is a kind of switch which goes from 0 to 1, no matter what the values of inputs are. So sigmoid function takes any number between any minus infinity to plus infinity, but it will squeeze that number between 0 to 1. So what is happening is that XT, the value of current input, and the value of past hidden state, they are controlling whether the gate should be open or closed. And by opening and closing, they are controlling the flow of information. And and again, what is happening? There is a cell state CT at time T. Then the information is added on that CT at the cell state. So it is kind of a train which is going, and whatever is needed to be learned is getting added in that. And there is a forget gate. So equation will make it clear that when the current input data is there, so it's not that you need to remember everything. I will give you an example. Again, I will give that example. You have a paragraph of text, and like in examination, there are this type of question that you have to read one paragraph, and after that there will be some questions and you have to answer them. So in order to answer some particular question, you may need not to focus on every word or every part of the paragraph. There will be some particular section which will be relevant for the answer, and that is kind of a learning. So here, this is exactly what is happening, that whenever we are reading any new thing, even the book, what we are doing is that we are updating our knowledge. That's one thing, which is the cell state. Every time a new data point comes, cell state is updated. Second thing is that when we get an input, we don't learn everything or we don't need to remember everything. We can have some part of it which we can forget, which may not be relevant for certain thing. So for that purpose, there is a forget gate. So it's in Word, but and here also there is a graphic. I think it should animation, but okay. Which gate is the forget gate? Yeah, you can see that forget gate. So this ht minus 1 xt, they are going to forget gate. Now forget gate will be updated. Either it will be on or off, and then it gives the information upward. And then the top, this horizontal line on top is the cell state. So whether it will add something on that cell state or it will not add, very much depend on what is the state of forget gate. If it is 0, then it will not add anything. If it is 1, it will add something. So let us look at the other gate. So now it is this gate, input gate. And here also the same thing is happening. In the cell state. So this animation is interesting to see, but equations make things much more cleaner. But I think this idea is clear. This basically what is happening is that these gates can be open and closed. And one more thing is that two of the gates are blue in color. So they have different activation, which is a 10H. So 10H goes from -1 to +1. And the sigmoid goes from 0 to 1. So when you are actually applying the 10H, then you may lower also the certain information. It's not 0 to 1. And output state is the same. Let us come to the equation. It's a bit very dense, so I will explain it and it will make things very clear. So there is a forget gate which depend on the input xt and past hidden state ht minus 1, and it has its own weight matrices. And so this input gate also has its own weight matrices, and state gate and output gate also. The only difference is that the state gate has 10H activation. So the value of C tilde T will be between -1 to +1. So when we get the input, the first thing is that we compute the states, their values. Once we have state values computed, then you can see the equation that CT equal to FT, and this is a element wise multiplication. I have made one operation which is dot inside a circle. So this is a element wise multiplication. If there are two vectors, so you multiply element by element to element and get another vector. I mean opposite to scalar product where you collapse and you get a single number. Okay, so two vector, this element wise multiplication gives them again a vector, and obviously they should be of the same shape. Like we are doing this ft and ct minus 1. So both of them will be of the same shape. So what we are doing in this equation, which is for ct, is that we are updating the cell state. So we have a forget gate and the past value of the this cell state. So this forget gate is actually forcing us to forget some information which is already there in the cell state. That's the first thing. Before adding new information, every time a new data point comes, we forget something. And the second part says that input gate, when input gate is open, then add the information on that from this CT tilde, which is computed up. And once this cell state is updated, we can get output from it by applying this 10 hyperbolic on this cell state. So let us see what is here. So in these 4 equations, we have 8 matrices and 4 vectors. So xt and ht minus 1 may have difference dimensionality. xt is the input vector. We can choose whatever dimensionality we want to use for it. And these cell state and the hidden state, they will have the size of latent dimension, the fixed dimensions where we are projecting our input text. So in that case, W will be a rectangular matrix, but U will be a square matrix. And the B will be of the same dimensionality as these two, WXT, so that they are added. LSTM number of parameters, how many parameters are there? N is the size of input vector, M is the size of hidden state, and dimensions of W is M into N, and dimensions of U is M into N. So this is in the code. All these Jupyter notebooks are available on the page, GitHub page. I have shared, you can see that. So this program here shows that how you compute the number of parameter in LSTM network. Last time also there is a question that how we are getting these parameters for the embedding layer. So in that case, this was just Vocabulary size multiplied by latent dimension. So similar calculation can be done here, and we can see that it has more number of parameters. So training LSTM network, every token word need to be represented by a dense vector of fixed size, latent dimensions. So what happens that before we feed our text to any LSTM unit, we need to vectorize it. And it is fine, we can vectorize it in one hot encoding way also, it will take care of that. Or we can add one embedding layer just before giving to the LST. So I have both type of examples available. I have already mentioned the size of the input vector X and hidden state H and memory state C can be different. So a useful property of the LSTM is that it learns to map an input sentence of variable length into a fixed size vector. So there are so many applications of LSTM. You can see that robot control, time series prediction, speech recognition, and many more, music composition. You can check more about it. And as I mentioned that from 1997 to up to few years back, these models, they have been ruling and people have developed many applications of it. I will give them very, very specific example later on. So on the basis of this LSTM unit, we can make a sequence to sequence model or sequence to sequence architecture. So these LSTM units are the basic building blocks of sequence to sequence model. So here is the paper of this sequence to sequence model. It's a very famous paper, again, very high citation, and these all, I mean, the first and second author, they are very high profile persons like Ilya Sutskever. He is the chief scientist of OpenAI, who is behind this ChatGPT and GPT. So up to that time, he was a researcher. He worked with Hinton in Canada, who is considered founding father of modern deep learning. And then basically the idea which he had from this sequence to sequence model and this exercise were taken further in terms of these transformer models and many other advanced models. So at that time they were working in Google. So this is the architecture. It's a very simple and very beautiful architecture, and which is still followed in GPT and many other models. So it is made of two components. One is encoder and second is called decoder. So sometimes it is called encoder decoder architecture also. Just two piece encoder and decoder. And it takes input output, as in any machine learning exercise we will do. We will have input, output, and then we will learn the model. But in this case, it can take two sequences at input as well as output. And we can train this model. So as I will go along while explain in detail, what is happening is that the weather is nice. So this is a word. This is a sequence of words. So when we pass these words to this encoder part, which is made of LSTM, so they update the memory state and cell state. So every time, like when the goes there, the cell state is updated. When the weather goes again, it is updated, and it is updated when the and so forth, till all the tokens are taken, eaten by this encoder, and then we will have a final state of this memory state and cell state. The final, when the final word goes in. So what is that memory state and cell state? Now what we do that we use that final state to trigger another piece called decoder, which will create the output sequence. So how it does that, the first word, obviously it will be difficult to predict. So first word we just starting word, we start with any word. Commonly there are start word. Now when this context vector, which is learned from the encoder, goes to decoder, then the first word will come out from this decoder output. Now this decoder output will come and the memory state of decoder will also change, also update. Now this updated state of decoder plus recently predicted word both go to the next state of this decoder, and the next word is predicted and the memory state is changed. So it is some kind of knitting thing we are doing together. We are updating the predicted word and the memory state. But here we do one thing during the training is called teacher forcing. So what happened that the decoder may not predict the correct word, but we already know what should be the correct word for the sentence. So actually we ignore the predicted word and give the correct word and they train the model. Until this keep going till we end up with a word which is like a stop word. So in the output sequence and the output language, there are some words which we learned that when they come, the sentence ends, end of the sentence word. So when the end of the sentence word comes, then we stop there and we go with the next sentence pair, I should say. So at a time, we take one sentence pair for the training, the next and so and so forth. So in this way, this model is trained. Trained means the weights are learned. So once we learn all the weights, we can use this architecture to predict sequences. So some of the common points about this sequence to sequence model, it's a deep learning based model. It uses LSTM or gated recurrent units. There are two components, encoder and decoder. And the modern generative AI, even attention and all these architecture, they also have this thing that they also have the encoder decoder. But their encoder decoder are not made of LST. All the processing is done in a sequence. Input vector of arbitrary length is mapped to a context vector of fixed by the fixed size by the encoder. Output sequence is generated by the decoder using the context vector and the passed output. Decoder is forced to predict the correct output. It's called teacher forcing. So there are many use cases of this sequence to sequence model. In 2020, Google released Meena, a 2.6 billion parameter sequence to sequence based chatbot trained on a 341 gigabyte data set. Google claimed that the chatbot has 1.7 times greater model capacity than the OpenAI GPT-2. It's till 2020 people were using this thing. In 2022, Amazon introduced Alexa TM2's 20 billion, a moderate size 20 billion parameter sequence to sequence language model. It uses an encoder to encoder decoder architecture basically, and it was some sort of competing with GPT-3. So it's not that these sequence to sequence model are completely out of business, they are still there. And this is TensorFlow Keras implementation where we have one encoder and we have a decoder. I will show the Jupyter notebook there. So this was the main paper. I have already shown it, and I mentioned it in last session that when we talk about the large language model, the first thing is that what do you mean by language model? So language models are nothing but some statistical model or maybe machine learning model which predict the probability of a certain sequence. If you have words like in English vocabulary 30, 40, and you make a sentence just with arbitrary word. So these language models would help you that what are the sentences which are correct. And if you put a condition, then they will tell you what should be the output sentence. Like in ChatGPT, when you ask a question, then it creates a sequence of tokens, but this sequence of token is conditioned by the question you ask. So essentially what we are trying to find out is that if there is a sequence of tokens, we are trying to find its probability. And for that purpose, whatever we use is called language model. These can be small, these can be large. So you can see that the same thing is repeated here, sequence to sequence model. There is an encoder and there is a decoder. So encoder, finally, a decoder gives us the output sequence. And one more important point is that we can create actually all kind of architecture. And there are some architecture where they use just encoder or they can use just decoder or they can use both. So there is a lot of possibility there. The same thing is there. You can see example. So the original paper, it discusses English to French translation. And it claims that it has found a very good performance of this translation. So there is few things I'm just this I already explained the teacher forcing what it is that during the training purpose from the decoder. So whatever the token is predicted, we don't use that, but we use the actual token. So this sequence to sequence model is some kind of starting point for the generative AI. Nowadays we talk a lot about generative AI, but this was the first generative AI model. Generative in the way that it was creative, it was able to create text and all those things which ChatGPT does. And later on, not only text, but this model was generalized on many other use cases also, including then video, music, pictures. So some of the text generation applications are question answering, machine translation, text summarization, grammar correction, story generation, conversational dialogue. Any task where system needs to produce text conditioned on some other text. Text generation along with large generation and code generation constitute a new area of AI that's called generative AI. And I particularly worked on one of the problems, as I was explaining to some of you, that we can use this sequence to sequence model for code also. Like on Git and GitHub, if you look at any commit, basic unit of data, let us consider it's a commit. So it will have a commit message. With that, it will have this red and green lines. So red lines which were deleted and green lines which were added. So what I did is that I scraped millions of commits from GitHub, from different repositories, particularly which have a large number of commits, and I created CSV files, column data. So where there will be the green part, red part, and the message. And then I try to use the sequence to sequence model on that data for the use cases like can we automatically generate the commit message for a commit, like you make a code change. And if you have a smart system like people already have at present, can it actually generate a commit message for that? Or at higher level, if there is a bug and there is a fix. So let us consider bug is also a sequence and fix is also a sequence. Can we train our model on that and predict the fix for any bug? So there were some challenges with it. One challenge is that source code is actually not a sequence of words or tokens as such. You can see that if you look at the code block in Python, Java, or any language, it has some structure and very non-linear structure. There can be jumps also. Suddenly there can be conditions also. So in that case, it is not correct to model a source code as a just sequence of tokens. Then what we did, we converted this source code into something called abstract syntax tree or AST. So where the code block can be converted into AST, and there comes that there is a version of LSTM, it's called tree LSTM. So someone has written a paper and the architecture is available. So this tree LSTM, what it does is that a tree is made of a root node and there are children. So in place of left to right, it can be like top to bottom, that there's a root node and that there are these children nodes. So we can consider that these multiple children of that node, they come first and the parent come later. So it is like these children parent. So it is kind of sequence, but in a non-linear structured way. So people are still using that. And then how to know that the text which has been generated is of good quality or acceptable? So for that, some clue is taken from human evaluator, how they evaluate some text or the translated text. And for that, there is a score called BLEU, BLEU. It's bilingual evaluation under study. So what it does is a very simple. We have a set of human written translation, good translation. Then we have one translation given by machine. We want to evaluate that machine translation against the list of human translations. And for that, we can do n-gram matching. We can do one unigram, bigram, trigram, and so forth. So I have not written that formula. It's a quite complex formula, but all these n-gram things can be used to match whether expectation is that if a machine translation is good, so at least it should have something common with the human translations. So they claimed in this sequence to sequence model that this model is very good and it can give higher BLEU score than the existing models at that time. So all the numbers are there in the paper. So now I end this theoretical part here, and I can take few questions, then I will show few Jupyter notebooks. So far, anyone has any question?
When you refer to cell, do you refer to one entire layer?
What is your question?
When you refer to a cell, do you refer to entire layer or is refer to single multiple layers combined together?
No, that architecture we can make. It depends on architecture.
So cell can have multiple like can it's up to us. We want to what we want to call as a cell. Okay.
Not exactly. The cells are already given in Keras TensorFlow. You can use multiple cells, and you generally do. I mean, you don't use just one LSTM cell. Just like a common neurons, you use many neurons and you stack them and you make the whole architecture. Even there is one example in Jupyter Notebook, I will share that GitHub repository, that it's possible to make a very complex architecture that Y sequence to sequence, you can make a model where there are multiple input and multiple output. Okay, and you can train such models also. Not just one sequence, there can be like 3 sequences going in and 4 sequences coming out.
For now, I'm using one sequence, one sentence, let's say.
Yeah.
One sequence is equal to one sentence. So this sentence is going in, 4 sentences.
So for example, it can be like there are 4 evaluators. Some candidate interview is happening. Okay, and they have their feedback. And we want to make a model which will predict the classification of the candidate. Either it goes to 0 or it goes to 1. So these 4 sentences coming from 4 evaluators, then we will need to put 4 inputs in parallel. And then network will then actually combine them and will give output. You understand that?
output is again sentences, not just the next word, next sequence.
Yeah, nesting. So we can have multiple sequences, or we can have multiple sequences also output. For example, we want to make a system which will give us uh, feedback about, for example, some travel advisory as well as some other advisory. So we want. So here are some of the simple to. So this is the basic example one which is there. It was to show that uh, how to find out how many parameters would be there. So firstly, we have input layer. In all the neural network model we make with Keras TensorFlow, the first layer is called input layer, and I am using a model called functional API model. So there is a sequential model also, but this is a functional API model. The first layer is input layer, and then we have LSTM layer, and then we have a model. You can see that it's just two-layer model, just a input layer, just LSTM model. And when we input dimensional is 20, and latent dimensional is 60. And then LSTM layer gives us three vectors. Three vectors, and all of them are like 60 dimensional. So as you can easily guess, these will be memory state, cell state, and output. And this is an example to where I actually make it as a classifier. So I am making model complex basically. The first one was very simple. Second, now I add one more layer. So what I do is the final, the 60, I was getting three vectors, each of one is 60 dimensionality. But I can reduce them using a dense layer to just two values, 0 and 1. And then can use that as a classifier. As it is done here. So input, look at the line number 23, 24. So what is my input? I am creating 1000 vectors. And then I am creating 1000 numbers, which are either 0 or 1. So I want to map these vectors to 0 or 1. So I have randomly assigned them labels, although there is a way to do the better way. And then I can train the model, and this is what I get. The loss decreases and the accuracy is not going very good. So because it's a random, I am assigning the random labels. But in one of the exercises, I actually what I do is that I add all the components of X and find out if the sum is even or odd. On the basis of that, I can assign some sensible label, and the model should be able to get that. Now I can use embedding also. So here line number 13, 14, and 15. 13 is the input layer just to consume the data. And then 14 is the embedding layer. So embedding layer, what it does is that it needs to know the number of tokens available in the vocabulary and latent dimension. So it does that. It's a large matrix of the size of vocabulary size multiplied by latent dimension. And then it gives us a vector of fixed size, which is of latent dimensions. And then I can do some normalization to that. And once my vector is ready, the XP vector, I can give that to the LSTM. And LSTM will give me output. So you can see that line number 16, LSTM unit gives me output H state and C state. And later on, I can consume just one of these states. So even if I want three labels, I can use separately this output state, H state and C state. So here is the architecture, and here was the input label. So I did the same thing here. At the last two lines, you can see here, this is the input data. And for this particular case, I created the label by adding all the numbers in the input vector and dividing them by 2 for finding out it's even or odd. So now I come to the sequence to sequence model. So basically what you do, you can write a pipeline in a very structured way. I generally prefer that. Like I have seen many examples on the internet where people just mess up with, they put everything in a notebook and very confusing way and it becomes difficult. So I follow this thing that modular, each block should be independent and if possible then in different files so that they can be correctly checked. And different modules should be doing different things. I always write one module which is called reading module. So that data may come from all kind of sources. And it may not be a good data, cleaning and all those things may be needed. So I write a separate program for that, where I will get the data, clean it, parse it, whatever I want to do it, and create a clear data of it, removing these special tokens and all kind of things. Second module I will write separately, which is my preprocessor, where I will build a vocabulary and I will vectorize the text. And again, that is also modular. And after that, when this thing is done, this preprocessor has converted my text into vectors. Then I can do the training. So machine learning part, I write two separate modules. Training module separate, inference module separate. So that there is no confusion. So the training module and the inference module should be decoupled. I mean, people generally don't differentiate that, but there's a huge difference on that. So in computing, if you look at the computing and data part, then 95% and more than that resources are taken by training instance or the training thing. So for training part, we may need very special kind of hardware and system. We may not be able to do training on any system. So it's better to write that training module completely different. If you follow the commercial online courses and all these things, they will not highlight this thing. They will talk about ML ops, like it's a software development process where step 1 to 10 all are equally easy or can need equal as the same time type of thing, but that's not the case. Even the team can be completely different. Machine learning training team can be completely different. Different kind of people can be there, and the inference people could be different. So it's very important to like training for GPT, Chat GPT was done with millions of dollars by some very specialized machine on somewhere. But inference we all are doing. So once you do the training, then neatly you can package your trained model in some file and you can pass those files. And the inference people or inference engine can use those. So these are some of the references. And I think I will stop here. This is the page for the course MLlearn 2023. So in this case, you can go through the text, what all you need. And as I mentioned that I plan to give 4 sessions and each one will be very rich and it may take time to consume that. Like this session 1, I gave this text vectorization. So there is presentation, there is video, then there are codes, and there are key papers. And then there is a tutorial and this. Now I will add entries to this sequence to sequence modeling, but I have already linked my GitHub repository of sequence to sequence here, which is this repository. So here also I have written a lot of text tutorial, and if you go here, so here I have written two program. One is sequence to sequence learning. I hope it opens here in. Yeah, it is opening here. So as I mentioned it, because it's a Jupyter notebook, I copied all the modules here. So this is a separate module. I write get data, and this data file you can find from my Kaggle page. So this is the data CSV file. English, French sentences are there. Then these two functions I put in this pre-processing part, pre-processing model I was talking about. So the first function does the vocabulary building work. It takes input text sentences and output as well. So here I am doing for both of the data together. in a loop, although I could do this thing separately also. Now I have a model called text to back. So it takes the text sentences and it takes the input vocabulary, and using that it can convert those into IDs. And again, you can see that there is some padding happening here. So if the vector becomes small, I pad it. If it's big, I shorten it. And this is the model. I generally write this type of model. You can check. So this model will have two parts. One is this constructor or initialize everything here, model building, and then it will be the fitting part. This fitting part, fit model part. So architecture can be added here. So let us look at the architecture, what is here. So the first part is the encoder. This is my encoder. So it has an encoder layer. This is a LSTM layer. And then it gives me encoder output, state H and state C. I have them ready. Then I create my decoder. So decoder also has an input layer. Then it has a LSTM layer. And then decoder output. And then I am interested in decoder output here mostly. So here these things are just blank here. And once my decoder output is ready, so I make the sequence to sequence model in this way. So what are the input thing are encoder inputs and decoder inputs as well as decoder output. So teacher forcing is taken here, but the decoder output is the actual output and decoder input is what is being predicted, and the fitting is done here. So we need to compile this thing where we need to specify what is the loss we are going to use and what is the optimization technique we are going to use. So both things are mentioned here. And after that, in the training part, I use something called callbacks. So 3 callbacks I mostly use. One is called TensorBoard. So it creates a visualization tool where we can see how the model was doing training and all those things. And then there is a checkpoint also where the trained model will be dumped. And this is the main program. Okay, you can see that this is how it is happening, and then I get the training in this part. So this is one, and there is an inference part. I am still working on it. Some part of it's done. So this is the Jupyter. So okay, let me explain at least theoretically what I am doing here. So for inference part, the first thing we need to do is that we read the trained model, and then we get the layers from that, whatever layers we need, the trained layers. And from these trained layers, we make something called encoder model and decoder model. We reconstruct. We could dump encoder and decoder model directly also, that will also help. But in this case, I'm actually reading them and building my encoder and decoder. So once I have the encoder and decoder, then I have a function called predict. So it will have input vectors, and then using the encoder and decoder, from the encoder it can create the memory state, and from decoder I can get the output. So that